Okay, so last week we had talked a bit about the discovery of the Higgs boson and what extremes we had to go to make that discovery. And that immediately gave us a number of questions. So the first was, well, what is the Higgs boson? Why did we have to go to such extremes to find it? Why was it worth spending all the resources and time and money doing it? And what do we do now that we found it? And so the whole point of these lectures, really the big picture, is to understand the answers to those questions. And so we started getting a bit at the why we're doing this in the first lecture. So we talked about this idea that all the things around us, everything in our everyday lives can be explained in terms of very simple scientific explanations. This was an idea that went back to Newton. And the amazing fact that it looks like that's happening, that program is successful. But it didn't seem that way in the turn of the 1900s. Okay, so we really hit a wall where we had this chain of explanations that sort of bottomed out at the level of chemistry, physics, other disciplines, where it wasn't clear that those talked to one another. So there were principles of chemistry that seemed to be independent of and unrelated to the principles of physics. And then there were these revolutions that happened in the early 20th century that really combined the two. And so we started talking about last week about the first of these revolutions. That was relativity. This was due to Einstein. And today we'll start with talking about quantum mechanics, so the second big revolution. So I made a wisecrack at the end last week that you could tell that it was more difficult because there were more people in the picture. And so to some extent that's really true. It took many more people than the relativity. It took longer. And the way you can think about that, why it was harder, is because relativity really took concepts that we knew already, that were familiar to science, space and time, and it was really about understanding how to think about them correctly, okay, and how to understand them. Well, with quantum mechanics, as we'll see, it was really not like that. It was a much more revolutionary change, and they really had to invent new concepts for how to explain the world. And so it wasn't clear at first which concepts to keep, which to throw out, and that took a lot of time to sort out. But remarkably, it's been sorted out. Okay, so again in the early 20th century, and it's understood. Okay, and it's really, in many ways, the most successful theory of science. Okay, and it's really the most successful theory for two reasons, in two different ways. One of the ways is sort of the nitty-gritty. So there's predictions that it can make about things that we can measure incredibly accurately, and when we measure those, it agrees with the predictions to 11 decimal places. So really, stunning accuracy in its predictions. So on one hand, it gets the nitty-gritty stuff right. On the other hand, it's able to explain very basic things about our world. So things are solid or wet, etc., that we would have a very hard time understanding otherwise. So it gets both the big picture, and we'll see some of this in the slides, correct, and the really detailed part. The other thing is it's not very difficult. Okay, it takes time to understand it, but it doesn't take advanced mathematics. Okay, so we're not going to go through all the details of it here, mainly because it's not relevant to the story. We'll only focus on the parts that are relevant. But if we needed to, we could. Okay, it's not something that you really need advanced theories or mathematics to understand. So despite these two facts, there's really a lot of nonsense written about quantum mechanics. So you'll see this probably on your Facebook feeds or in local media, people saying that quantum mechanics is wrong, they have a better idea for it. But it's really nonsense. So everyone that uses quantum mechanics, so physicists, chemists, nuclear engineers, they all agree that the theory is correct, and they all agree how to apply the theory. Okay? So it's really a settled matter. There are people within the field that are trying to apply quantum mechanics all at once to the whole universe. Okay? So there's some open questions about how to do that, and there are people considering modifying it in that context. But even people scientists that do that agree that outside of that very specific context, the theory is correct and how it's applied to everything else. Okay, so Right. So, but there are doubts about its interpretation. Okay. So the theory itself is well understood, but how to translate that into a human language or human concepts is not understood. Okay. There's big disagreements even within the field on how to do this, and this shouldn't come as a surprise. It's very difficult to do this translation, and that's mainly because our brains are not hardwired to understand quantum mechanics. Okay. As we'll see in this talk, it would have done our ancestors in the jungle no good to know the detailed principles of quantum mechanics. It wouldn't help them survive. And in fact, it probably would have hurt them a lot. Right? There's a big cost to developing a brain that could understand that. And it wouldn't, we have a stereotypical vision of the scrawny scientist that doesn't get many opportunities to reproduce. Right? He would have gotten eaten by the lion. Okay? So it would have been bad for us to have this intuition, or to have developed this intuition of quantum mechanics. Okay, so the interpretations are really an open issue. There's a lot of activity. There's a lot of literature on that. I'm not going to talk about that at all here, mainly because it's not relevant to our story. So it's something that I think is really more in philosophy or even psychology. It's more about us trying to understand quantum mechanics than about the theory. Everyone is in agreement on the theory. It's just how we make it, build an intuition for it. So that doesn't mean I'm not interested in this stuff. It's just that it's solving that problem is not how you make progress in science, even in something as esoteric as the Higgs boson. So I won't discuss that. Here, I'll only focus on stuff that's relevant to the story that we talked about. Okay, so moving on. So that's enough of the prologue. So quantum mechanics really came about from trying to understand the atom, okay, and structure in the world around the turn of the 20th century. So we had developed this picture of what an atom was, and we knew it was made of two different pieces. So there were electrons that were negatively charged, and there was a nucleus that was positively charged, and it was the electromagnetic attraction that kept the two together. And so it was understood that the electron really took up most of the space of the atom, okay, and it sort of orbited the central core, which was the nucleus, that made most of the mass of the atom, okay. And it's an inverse square law, just like gravity. So it was thought at the time that you would get orbits of the electron around the nucleus, just like planets around the sun. So it was confusing because if you applied the theory to this picture of electrons orbiting the nucleus, you'd very quickly predict that the electron should spiral in towards the nucleus. Okay, it should be unstable. All right, so the planets are stable because they're revolving around the sun in a vacuum. There's really nothing there. But with an atom, there's light everywhere, right? And so light could scatter off the electron, and you predict that it would lose energy very rapidly, and matter would be unstable. Okay, but of course matter is stable, so that was something that was very confusing. A closely related problem is how atoms were seen to interact with light. So they could exchange energy in the form of light, and the theory at the time would predict that it should be able to do this at any frequency or at any amount of energy or of light of any color. Okay, so we would expect the whole spectrum of light to be able to interact, and that was not observed. It was observed, you'll see this in the next slide. It was only observed for very discrete values or very particular colors that changed depending on what particular atom you were looking at. And that wasn't understood at all. And third, there was another mystery of waves and particles. So there were things that behaved like particles, like baseballs and bricks and things. And then there were things that more naturally behaved like waves. So like light, for instance, was very wave-like. And it was a riddle that, are there really both two ways of existing, or is one more fundamental than the other? And this was something that was also unsettling and was not clear. Okay, so these are really the problems that people were facing. Here's an example of the interaction of light with atoms that I was talking about. You would expect all the colors to appear, any of these to interact with an atom, but the chemists in particular observed that this could only happen at very particular wavelengths, depending on which atom it was. And they actually used this a lot. So this was an example of a case where it was thought that really chemistry was separated in a way from physics. So physics couldn't explain why you would have these fingerprints for atoms, but chemists used them and they were able to identify what a certain substance was made of by looking at these lines. Okay, so there was really a long period of confusion. Okay, there was a lot of partial progress. As I said, people were throwing out what came before, really in a revolutionary way. And so this took a long time. So there were competing ideas that were able to give partial answers to some of the questions. So they were able to predict some of the spectra for very simple atoms, but not the more complicated ones. But eventually, there was a unified and consistent theory was reached. And the solution, you may think, naively, the solution has to be either the way that we're thinking about the atom is different. It's not really an electron circulating, orbiting the nucleus, or maybe the electromagnetic interaction needs to be modified, the force holding it together. But it was really neither of those that was the solution. There was really a completely new framework for all of physical phenomena. Okay, so really kind of radical departure. And as I mentioned, it's not a complicated theory, but we're not going to go through all the details. I'll just give the upshot here. Basically, the idea was that you shouldn't talk about or even think about the trajectory of an electron within the atom. Okay. Instead, what was fundamental, or what exists in reality, is this new idea, the mathematical concept that's called the amplitude. Okay, and that was traditionally called psi here. And so psi is really the fundamental entity, okay? And it describes everything there is to know about a particular situation. So in particular about the electron in an atom. And the theory tells us what these amplitudes are. Okay? It tells you what the psi is. It also tells you how they evolve in time. Okay? So if you know what psi is at one time, it predicts what it will be at a different time, okay, and it behaves very much like waves, wave equation. And it also gave probabilities, formalism to convert these psi's, which are abstract things, into probabilities for what we observe, okay. And the way that's done is you just square this amplitude to get the probability for something to happen. Okay, so I'll talk about the features that were really different with this than what came before. The first is this thing of probability. So what do I mean by that? So quantum mechanics tells us that there really is this inherent randomness in nature. Okay? If you remember, we talked about the physics before the revolution last lecture, and there was this notion that if you knew everything that was happening at a given time, then in principle you could predict what would happen at any other time, forward or in the past. With quantum mechanics, that's out the window. Now you can only it's only probabilities that one can predict. And so, for example, if we have two muons here, we talked a bit about muons last week, but they're particles, if they have the exact same wave function, okay, or the exact same amplitude, it's often called a wave function, you can get different things. So this one can decay, so the muon can explode into 3 particles. Don't worry about what these are at the moment. They could do this in 2.1 microseconds with a certain angle. Okay, and a different muon that again has the exact same fundamental amplitude can give a different result. So it's a different, lasts a bit longer, and there's this angle is different. Okay, so it's really only the probabilities that can be explained. So we can't say what will happen in any particular case. So in any particular event or any particular muon decay, we can't say exactly what will happen. We can only say what will happen on average. Okay, and we can only predict distributions of large numbers of these events. And so this was really a huge loss in productivity, right? So before, everything in principle we could predict. Now it's only averages. Okay, so that's one of the big upshots. Another of the big upshots goes on the term the uncertainty principle. I'll just explain a bit what that is. This is really key to what we'll be talking about later. So this is the picture before that we talked about last time. So remember, time is going up in this direction and some space in this direction. So if you have a particle that's moving, it's just a straight line. Okay, and so this period before quantum mechanics is often called the classical period, or classically. That means without quantum mechanics principles. So this was the picture we had before. And in particular, we could know, where this particle was and what direction it was moving to arbitrarily accuracy. So we knew both this angle and its location. Now, one of the things that quantum mechanics taught us is that this is not possible, even in principle, to know both of these. Okay, so instead of drawing those lines like we had in the previous slide, we should only be thinking about things that look like these triangles. Okay, so if we know very precisely where a particle is at one time, then there's an inherent uncertainty in which direction it's moving. Okay, and this is something that we just can't know both of these at the same time. Okay, and so another way that this can manifest itself is if we know this angle very precisely. So we know, very accurately which, its movement, then we don't understand, there's a big uncertainty in its position. Okay, so instead of drawing a line, the lines have to be either fat lines like this, or they have to be triangles like this. We can't know both of these quantities at the same time. And so, to give a little mental picture, if you have a muon that's sitting here, you should think that there is some fuzz or some inherent uncertainty in both where it is and which direction it's moving. Okay, this uncertainty relation shown here, this delta x is the uncertainty in x times the uncertainty in the momentum or the direction it's moving is bounded by some fundamental constant in nature. Okay, so we can't know both of these arbitrarily accurately. And if you know one very precisely, then you don't know the other. Okay, and there's an equivalent relation that's closely related to this in terms of energy and time. So if you know very accurately the time that something occurred, there's an inherent uncertainty in the energy that process had, and vice versa. Okay, and so I want to stress that this is really not. It's not that we just aren't good at measuring both of these at the same time, or that we have some problem. The theory has some problem describing them. It's really that they're incompatible. They're incompatible notions, and so I'll try to talk about that on the next slide. So here's what one of these wave functions would look like, or these amplitudes would look like. So they're really sharply well-defined quantities. It's not like there's uncertainty in what these things are. So here's an example of, now I'm showing what this amplitude looks like as a function of space. Okay, this is an example of an amplitude that has a very well-defined position. So when you know the position, it looks like this. It's peaked at a particular value in space. Okay, and so that means that the probability, which is just the square of this thing, is sharply peaked at one place. Okay, so whatever, let's say the muon is with very high probability, it's located right here. Okay, a wave function that has well-defined momentum looks more like this. Okay, and so the momentum is well-defined when the distance between peaks is uniform. So when this distance is the same as that distance, etc. So you can see that these are totally incompatible, right? And in space, it's well-defined when there's only one peak. Okay, and in momentum, the notion of momentum requires multiple peaks. Okay, so if you have the spacing, the spacing between peaks is constant, then necessarily there are more than one peaks. Okay, and so another way you can think about that is this momentum, this wave function that has well-defined momentum is sort of made of little pieces that are well-defined in space. So you have to take these and add them together to get something that's well-defined in momentum. Okay, and the same thing works the other way. So here's an example of taking things that have well-defined momentum. So the spacing between these peaks is the constant in all these individual waves. And if you would add them all up, you would get something that's more localized in space. Okay, so again, something that is peaked in one place is really the sum of things that have different momentum. So the distance between peaks is related to what the value of the momentum is. So you can see that they're really incompatible notions. So it's not that well, we just don't know really what the position and momentum is. It's that they're just opposite notions. Okay, so for most particles, we actually know reasonably well where the thing is located, and we know reasonably well what its motion is. So those amplitudes tend to look like this. Right? So it's located roughly here. Right? It has very small probability to be outside of this, and the spacing between these peaks is relatively uniform. Okay, so this is really what we're dealing with normally, but you can see that it's you can't know both at the same time. They're incompatible notions. Okay, so it's really this basic thing that has many implications our field. So I'll highlight these briefly. One is just the basic stability of matter. So this issue of the uncertainty principle is responsible for stabilizing, for solving this riddle of why atoms are stable. And so here's our picture of the atom with a let's say this is hydrogen, so it's just a proton and an electron. Classically, so again, before quantum mechanics, the energy associated with this is just given by the electromagnetic energy. And so you'd expect that this electron should be attracted immediately to the proton and should be as close as possible. Okay, so just in pictures, this is showing the energy that wants to be at its lowest value that it can as a function of the distance of the electron from the proton, so this distance here. And without quantum mechanics, and the thing that was such a big puzzle before it, was that the minimum was as close, it was basically right on top, with this R goes to 0. Okay? So the electron will always sit on nucleus. There would be no volume to any of the atoms at all, and they would just sit directly on top of one another. But with quantum mechanics, this is solved by this exact uncertainty principle. So what happens here is, again, for large distances, it's the same form. So it's just the energy of the electromagnetic interaction. But when you get very small values of radius, then its position is well localized, right? So we know its position very accurately, which means we don't know what its momentum by this uncertainty relation. So there's a bound. If we know this, the relation we saw before was delta R times delta P is greater than some number. But you could write it a different way, where the delta P is greater than this number divided by the uncertainty in its position R. So when R is really small and very precisely there, like would be in the case classically, there would be a very big uncertainty in its momentum. Okay? And that's a form of energy. So in a quantum world, one has to take both of these into account. And when that happens, there's a minimum. Right? At very low values, the quantum mechanical energy dominates. At high values, it's the electromagnetic. And intermediate, there's a stable point. And this gives the size of atoms. Okay? So it's really, quantum mechanics, considering both of these effects, predicts that there's a finite size of the atom and actually gets to this value. Right? Okay, so that's one consequence of the uncertainty principle. Another has to do with minimum energies. Okay? So here's an example that highlights that. So here's a situation where I have a ball that's hanging from a string, okay? And so this thing can oscillate around here, right? And so there's two forms of energy. There's energy of its motion. So when it's down here and it's moving, it has kinetic energy or energy of motion. When it's up here at the top of its swing, it has what we call potential energy. So it's not at equilibrium, and it will tend to swing down. So it has both of these components. So that's just show there. In a classical world, without quantum mechanics, the lowest energy configuration of this is 0. So the thing is just hanging here, it's not moving, and it's not displaced from the straight line. So it really has 0 energy. In a quantum world, this isn't possible. Again, from this basic uncertainty principle. If you know that it's located here very accurately, you don't understand. There's an inherent uncertainty in its momentum. So there's some jiggle in how much it's moving. Okay, so it cannot be both at the lowest point and not moving. Right? That's just the same statement as the uncertainty principle. So that means there's some inherent motion always with this, and the minimum non-zero energy is not 0. It's some value that's related to how the frequency at which the pendulum would oscillate. Okay, so two big dramatic differences already with quantum mechanics. The other, it also solved this riddle about waves and particles. Okay, so it came down on the side of particles. So everything is a particle, but everything is a quantum particle. So everything is a particle that obeys the laws of quantum mechanics, and so those are different from the particles that we know classically, like bricks or balls. So particles have definite values of mass. They also have something called spin. So this is like you can think of it as like the rotation of the Earth, say, or of a ball rotating. Particles possess a quantity that's similar to that has values that they can't be anything. They have to be quantized. So this is one of the reasons it's called quantum mechanics. These can't take on any value at once. They have to be half integers. So they can be 0, 1/2, 1, and this can go arbitrarily high, and units of this fundamental constant. And they can have other properties. Okay, so they can have charges, other things that are also quantized. So another really dramatic difference with quantum mechanics is when you have two particles that have the same, that look the same. So let's say you have two electrons here that are moving. In a classical position, when these overlap, at this point you know the position and momentum of both of them, right? And so you can actually say that this one came from here, this one came from here. Okay, so you can follow these trajectories back in time, and you can put labels on these. So you can say this particle is there, this one's P1, P2. In a quantum world, again, at this point, you don't know both where it is and how it's moving. So we have to draw these little triangles instead of the arrows, or instead of the lines. And in particular, when they overlap, you don't know for either of these precisely where it is and how it's moving. Okay, there's some inherent uncertainty in that. And so that means that if you tried to label these at a certain time where you knew where they were in space, and allowed them to interact in some way or cross paths, then at a later time, you wouldn't know which one is which. Okay, so even in principle, you can't tell, did this one go like that, or did this one go here? Okay, so there's just no way of following those trajectories back in quantum mechanics. So that's why I say here, and that means that the theory has to, so particles that are identical, so if they're two electrons, they must be treated as indistinguishable. So the theory has to be the same. It can't matter which electron you call which. Okay, they're all indistinguishable. And so that has big consequences. Okay, and so we saw that the physics depends on the square of this amplitude. So that's all the probabilities of observing things. If this amplitude depends on two particles that are the same, so two electrons, P1 and P2, then this square has to be the same if you switch them, right? Because it can't depend on your labeling of what they are. So these two have to be the same. And that means that when you switch the order of these in this amplitude, you have to get the same value back, okay, up to a sign, relative sign, right? If you get the positive, if they're really the same, if the amplitude is the same, then of course the square is also the same. If the amplitude is the same but with a minus sign, when you square it, that minus sign will turn into a plus sign. So you have two minuses and pluses. So you have this relationship that has to be obeyed. So there's really two types of particles. There's particles that we call fermions, named after Enrico Fermi, that when you switch the position of these, the amplitude picks up a minus sign. And there's another type of particle that if you switch the ordering, you don't get the minus sign. Okay, and so the realization is that everything is a quantum particle, and particles that are big collections of fermions, so things that behave this way, act like classical particles. So these are things that act like bricks or baseballs when you have large collections of them. And quantum particles that are bosons, so that have the same sign, act like classical waves. So really everything is a particle, and the distinction between waves and particles comes down to this. Okay, so it's really, but again, you can think of it, it's really from the uncertainty principle and the fact that we cannot trace trajectories in space and time that is giving us this. Okay, so I mentioned at the beginning that these quantum effects aren't relevant in our everyday lives, and they certainly weren't relevant for our distant ancestors. So that's true also of relativity, right? And so you'll often see people saying that relativity is wrong too. And again, some of the notions of relativity are hard for us to understand intuitively because for the same reasons that knowing relativity would not have been an advantage to our very distant ancestors. And so just to give it, so the reason why that is that C is a really big number. So this upper limit, for practical purposes, is not really a constraint for us. Okay, so C is about 500 million miles per hour, right? And so in our everyday lives, we're never moving that fast. So the fact that there is an upper limit doesn't really matter. In quantum mechanics, everything comes down to this new limit on the uncertainties. Okay, and this is also a very small number. Okay, so don't worry about this detail too much. I'll show why. I'll show how to think about this in a second. So here's example. So we saw last week that if you move fast, you could trade time for space, right? And so we have this effect of time dilation, or the fact that things could appear to live longer than they would if they were at rest. And so here's an example. If I, or maybe my distant ancestor in the jungle, could move at the speed of an airplane, so as fast as I can move, 500 miles an hour for 80 years, they probably didn't live that long back then. If they did this, they would gain 1 millisecond. Okay, so that's not a big advantage. The jungle. Similarly, for quantum mechanics, we have this notion of there's an uncertainty in, if you know the position very accurately, there's an uncertainty in how you're moving. So if our ancestors knew their position to the size of an atom, okay, which is way more than they needed to see to know where the line is, if it's going to get them, this would correspond to an uncertainty in how fast it's moving of 10 to the minus 26 miles per hour. Okay, so that's 0.000 with 26 zeros followed by 1 miles per hour. So again, not very important. So this is why these features that seem very bizarre that are true are not apparent to us in our everyday lives. Okay, so just to close on this, on these two revolutions, there was actually a particular nature of the revolutions in science. So it really wasn't that we took everything that was before and just threw it out and said it was totally incorrect. All the theories that came before were seen as an approximations in a certain context. So when you're not moving very quickly relative to this upper limit, or when you know the positions and momentum, you only need to know them much less precisely than this inherent upper limit. The theories that we had before are accurate, they're correct, and they're valid approximations. Okay, so that's one of the natures of these revolutions. So it's really building on what came before. It's not like everything was thrown away. The other thing that, at least very qualitatively, is progress brings greater unification. So concepts that were very different, that seemed very different before, were seen to be aspects of the same thing. So in relativity, that's from space and time. We saw that those were closely related. They're really the same thing in an extent. And also with these waves and particles, classical waves and particles are seen to be aspects of the same underlying quantum particle. Okay. It also brought us a loss in predictivity, okay, which is interesting, and that's another theme that we'll come back to. Okay, so here's just examples of things that were thought different. So space and time, as I said, also energy and mass and momentum are seen to be the aspects of the same thing, closely related to one another. We didn't talk about this, but also electricity and magnetism. Something that looks like it's an electric force in one reference frame. If you're moving, it looks like magnetism. And also Einstein actually went on to show that gravity can also be thought of as a warping of space and time. This we won't really talk about too much, but it was also a big unification there as well. And in quantum mechanics, unified waves and particles, as we've just seen, but also these, it can now explain all the phenomena of chemistry in terms of the behavior of atoms that are now predicted based on the principles of quantum mechanics. So again, big unification. Okay, so that was really, in a sense, part of this first lecture of setting the stage. And so now I'll move to this, to the second piece. What I want to talk mainly about today is the mission. It's called Mission Barely Possible. Okay, and so this is combining both of these revolutions. Okay. So reminder, you won't need much of this. You just saw it. But with relativity, we have this notion of space-time, right? That really that if something lives in this position, so at this time, to another observer that's moving, it can live anywhere on here, okay? And similarly here, if you have something that to one observer looks like it's located here in space and time, to another observer that's moving, it can live anywhere on these invariants. So that we went over last time. We also talked about how mass increases with speed when you're close to the speed of light. And closely related to this, almost the exact same argument is that energy is related to mass. Okay, so you're by increasing the energy, you have to increase your mass at some point. And then there's a generalization of this that you'll often see. So this is the famous one, right? But really, your energy squared is equal to the EMC squared, so this piece. But also, if you're moving, you have some energy, of course. And so the more general form is there. Okay, quantum mechanics. This you don't need a reminder because we went over today. But again, the highlights is you have this new concept that's the amplitude, and the theory tells us how these amplitudes evolve in time. Okay, so they behave like waves. We square them to get the probabilities. Determinism is gone, so we can't predict in any particular case what's going to happen. We can only predict the probabilities. And we have these uncertainty principles that have big implications, right? In particular, there's the minimum energy is not zero, and it gives these two types of particles, fermions and bosons, that depend on where the sign changes. Okay, if you interchange them, and we saw that, or just told you that this notion of spin, how fast you're moving, is quantized, and it's in half integer values. Okay, so another thing I should say is really the first half of the 20th century was all about revolution, right? So we had to come up with new notions of space and time. We had to come up with totally new notions as amplitude in quantum mechanics. But that happened really in the first 25 years. And all the progress since then, or all the work since then, is really understanding how to put these two together. So that's really where the progress has been. And it's not always about revolution. Okay? So as we'll see, there's places where it looks like this is impossible to do. And you might say, well, we need another revolution. We need to throw everything out again, come up with new physical principles. But that's not the case. Really, it was about thinking more deeply about relativity and quantum mechanics. So it was being conservative in a way of taking the principles seriously and trying to combine them. So it's not always revolutionary physics. And in fact, for most of it, it's not been throwing things away. It's been taking what we have and understanding them more deeply. Okay, so combining this looks to be impossible. Okay, so at first look, you would say there's no hope in doing it. Okay, and that's because the basic languages are different. And so what do I mean by that? So in quantum mechanics, there's really time is special. Okay, there's this fundamental rule of time. So you specify what the amplitude is at one particular time. Okay, and there's a prescription for how it changes in time. Right? So you see, time has a very critical role. Whereas relativity taught us that time is not special, right? That one person moving, it looks like the light hit the wall earlier or later, or at the same time, or they're not at the same time. And so relativity says that you can really trade time for space just by moving. So it looks like these are inherently incompatible. It turns out that it is almost impossible. It's just barely possible, okay? And making it possible really restricts what types of things are allowed. We'll see that in the following. And what came out of this union of these two is something that we call quantum field theory. This is taking the quantum mechanics and making it consistent with the principles of relativity. And this is really the basic framework for how the world works, okay? And it's not only the basic framework for how our world works, our particular world, and I'll talk about this in the next lecture, it's really how any possible, conceivable world would work that obeys the principles of relativity and quantum mechanics. Okay, so it's really sort of a general rubric or framework or language for how we can describe reality. Okay, again, so we saw that both relativity and quantum mechanics reduced what we could talk about. We can only talk about probabilities. We can't talk about both position and time. Combining these is another dramatically restricts what the theory could possibly look like, even in much more dramatic ways. And we'll see that in this talk. Okay, so just very quickly, some consequences of the union. I'll talk about some of these more in detail next slides. The first shocking, unexpected consequence is that antiparticles must exist. Okay, so there must be this notion of antimatter, that every particle that exists has a partner. And I'll talk about that. So this basically doubles everything in the universe. Okay, or at least doubles the number of particles in the universe. And it also has an interesting thing that makes the vacuum interesting. And so I'll talk about what that means. This notion of spin that I mentioned in quantum mechanics that could be half units, this really takes on a life of its own in the relativistic version of quantum mechanics. So there's a strict relationship between the spin and the particle type, whether it's a fermion or a boson, and it dramatically limits the types of particles that we could have, and we'll see that as well. There's also major constraints on the type of interactions that are allowed. So in general, the fact that time is special means it's not going to obey quantum mechanics, or vice versa. But for certain interactions, they look the same to everyone, no matter how you're moving. But that has a major restriction on the types of interactions that are allowed. Okay, so there's only very certain types that are allowed, and we'll talk about what that means. But it also has the conclusion that there's only a finite number of numbers that we need to know in any given theory. That will be the subject of the next lecture. Okay, so I'm going to talk about antiparticles now. So quantum mechanics says that determinism is no longer there. Okay, but there's causality. Okay, this is really important to have. This is just the notion of what happens next can only depend on what happened before. Okay, so that means what happens at a certain time doesn't depend on something that hasn't happened yet. Okay, so this is really a basic prerequisite to doing science. Okay, so an example of that is if someone dies from a gunshot, then the gun has to be shot first. Okay, it would make no sense if it was otherwise. So what about causality and relativity? Okay, so we talked a lot about the fact you can't send particles or signals faster than this maximum speed. That was the basic input to the theory. And so here's an example of something that happens at one time, and then at a later time something else happens. Okay, so this you could think of it as maybe a gunshot. Okay, so here the gun goes off, here it hits somebody. And we saw that by an observer that's moving might see this at a different point in time, right? But luckily these things live on the curves that we went over last time. So someone that's moving, this point B could live at a different place, but it has to be along this invariant. But this is good because everybody agrees, no matter how you're moving, you might disagree on what time the thing happened or where it happened in space. Everybody agrees that what happened on B on this line happens after A. Okay? So causality is okay in relativity. So all observers, so that's why I say A happens before B, so we can safely say that A causes B in this case. Okay, so in just normal relativity, causality is fine. But things, there's good reason you can't go faster than this upper limit. If you could, then things would go wrong. Okay? And so here's an example of something that can't happen, but if it could, in relativity, something goes faster than this maximum speed. Now the invariant looks like this. Okay? And so different observers, people that are moving different ways, it can live anywhere here. So now it looks like causality is violent, because if this happens, someone that's moving in the other direction at a very high speed might think it happened like this. Okay? And so that means that the bullet, to him, the bullet hits the guy before A even shoots him. Okay? So causality is violated if you could get out here, you would violate causality. Okay, now here comes quantum mechanics. So now you try to put quantum mechanics into this picture, and it looks like a disaster. Okay, so again, for this, it's always the same sorts of arguments. This comes back to this uncertainty principle. So we can't draw the lines before. We have to draw things that have width. And so if you do that, there's always if you have something here, you can't precisely localize that it's happening exactly there in space. There's always this quantum mechanical uncertainty from the uncertainty principle. And so that amounts to there's always some probability that it gets out. Now this probability is small. It's set by that really small number, but it exists. Okay, it's non-zero. So we say when this happens, we say it gets out of the light cone. Okay, that's the fancy way to say that, but that's really what it means. Now this is, just for the same reason that you would think this is a disaster. Okay, so if let's say particle A, now everything's quantum mechanical. So let's say it shoots a proton, okay, instead of a bullet to B. There's a probability that this happens. Okay, so you can't really see this, but this is a red arrow that's going from A to B. Okay, so there's a small probability that this occurs. Now, of course, if someone that's moving very fast in the other direction, or in It can live anywhere here by relativity. So somebody that's moving could see this happen, right? So this red arrow is coming from A to B. So now it looks like this proton hits B before A sends it. Okay, so now this is a point where you could give up. You could say it's hopeless. You can't combine these two, and so we need another revolution. We need to throw everything away and start again. And that was the answer with quantum mechanics, but since then that's not been the answer. The answer has been to really understand what's happening here harder and see if you can interpret it in a way that's consistent with both of these basic principles. And so that's what was done. And so what you could do is you could interpret. So it looks like so the person that's moving could say, no, I think there's something that's going from B to A. Okay. So they can interpret it like this. There's another arrow, but it's not violating causality. It's going forward in time. But something that we know is that the proton has positive charge, right? And so in this picture, we know that whatever happened, A lost charge and B gained charge. Okay, so there's a net flow of charge in this direction. Now, of course, the observer that's moving agrees that happened too. He knows that the charge at A went down. So he's going to interpret this as something from B going to A. He has to see this as a particle moving that has the opposite charge of the proton. Okay? And now, of course, it doesn't matter that it's a proton. This could be an electron or whatever. And so there's a way out. So there's a way to preserve causality if this person that's moving says it's actually B is sending something to A with the opposite charge. Okay? And so this is antiparticles. Okay? And this is just a schematic picture of why this has to happen. But this, in detail, if you work it out, this is almost exactly what happens in the theory itself. Okay, so particles that must exist that are identical in every way. They have the same mass. They have all the other things are the same, spin, etc., except they have the opposite charge. Okay, and it's really for this basic reason of causality. So everybody has to have a partner, and we call that partner that has opposite charge antiparticles. Okay, so now this has an important impact on nothing. Okay, and what do I mean by on nothing? I don't mean really on nothing. I mean on empty space. Okay, where we call it. Physicists call empty space the vacuum. And so this means, okay, so if you think about what does it take to understand empty space, okay, to study empty space, well, it doesn't take anything special, right? If you don't know what's in a room, you can turn the light on and look what's in the room, or you can go in the room and feel around. So it's really easy to study empty space until you try to get down to really small regions of space. Okay, and so it's always the same thing here. Okay, so before quantum mechanics, if you wanted to study really small regions of space, what you could do is you could look very closely, but at some point, even your magnifying glass or microscope breaks down, so you can build a tiny robot to explore it for you. Okay, so you can build some small thing. If that wasn't good enough, you could have the robot build even tinier robots. Okay, to build even tinier robots and tell you what's happening in small space. Okay? And so without quantum mechanics, you could do this, right? This could be done. With quantum mechanics, this uncertainty principle kicks in again. So as you make things smaller and smaller, these robots, if you know that they're very small, it takes a huge amount of energy to keep them from blowing apart, right? Because the uncertainty on how the pieces they're made of is very, very large. So they have extremely large energies, and it gets to the point where the atomic forces can't keep those tiny robots together. So we literally can't make machines or robots or any devices as small as we like because they eventually blow themselves apart by the uncertainty principle. So it's smaller. So that's why I say here, small distances. It's really this uncertainty principle again that kicks in. And so to really go to small positions or small delta x, we need very large delta p. Okay, and so another way of saying that, at smaller and smaller distances, you need higher and higher energies. Okay, so it's to the point where we can't just build objects. So what we do is we shoot things together. So that's like light. So when you turn on the light in the empty room, you shoot photons around. Talk about that more precisely in the next slide. But that's really the intuition. You need to put energy. You need to put energy in a small. You need to put a lot of energy in this space if you want to probe very small spaces, just by this basic uncertainty principle. And this turns out to make empty space very interesting. So if you put, so you want to go smaller and smaller in space, so you're putting more and more energy in, and eventually you get to the point where the amount of energy you need to probe a certain distance equals twice the electron mass. So 2m MEC squared. So when you do this, nothing prevents you from, with that energy, to creating an electron-anti-electron pair. Okay? None of the laws of physics are violated. So particular energy is conserved because it's the same energy as you're putting in. Charge is conserved because we have antiparticles. And quantum mechanics says that there's some probability for this to happen. Okay? And there, it doesn't always happen when you do this, but there's some probability for it. And it's non-zero. Okay? So just the act of looking at a small enough region, if the energy is bigger than this, the energy it would take to make an electron, pairs of electrons, or electron and anti-electron, just the act of looking would create these electron, anti-electron pairs. So this really completely changes our picture of the vacuum. Okay? So the simple act of what I said, just by trying to look at it, you create something. So you think it's empty, you want to verify that it's empty, you have to put energy in to do that, and that act creates things. So there's really no sense, there's no useful sense in which the vacuum is empty. Anytime you would try to verify that it's empty, you end up creating things. Okay, now of course, if this is, the electron is one of the lightest things we can make. If you want to look at even smaller distances, this energy becomes big enough to create protons or muons or other things that are heavier. Okay, so when you get down to those distances, you create electrons and you create these other things. So really, what's in empty space depends on the scale that you're looking, and we'll also see how you're looking. Okay, so in the press, we often say, maybe I'll just go through this and we'll come back to the question.
How come then that we can't calculate vacuum energy?
So I'll come back to that now. So the question was, how come we can't calculate vacuum energy? That's a very deep question that we'll come back to. So in the press, you often hear people say that accelerators are like the world's most powerful microscopes. Okay, so I have friends that work with microscopes, and they ask, what the hell are you talking about? What is it looking at? Right? And the answer is it's looking at the vacuum. Okay, so it's taking detailed pictures of the vacuum. That's the whole point of these accelerators. And of course, you'll get a different picture each time you look because of quantum mechanics. There's probability for things to happen. And the pictures, we do the same thing over and over again, but the pictures are different. And what the pictures are, in a really sharp sense, they're pictures of how the vacuum is behaving. Okay, so this is I'm just finishing up here, last slide. So there's other implications for combining relativity and quantum mechanics. And so I said when you're just dealing with quantum mechanics, the mathematics isn't that hard, and it's fairly easy to understand. When you try to combine these, mathematics does get very difficult, and so we need to go to grad school to understand a lot of these in detail. But it's not, again, it's not mathematics that's totally far out, right? It's things that mathematicians were studying hundreds of years before, but it's not something that we can go through in 10 lectures here. So I'll just state the results. Okay. So with just quantum mechanics, okay. The situation for spin was you could accommodate, it could accommodate spin, right? You could describe, particles could have spin, but if they had spin, it had to be half integer values. You could be 0, a half, 1 half, 1, 1 and a half, etc. And it could go as high as you wanted. And then we didn't talk about this explicitly, but any conceivable interaction was possible. So you could write down whatever, however you wanted, this particle interacts with that particle, however you'd like. When you combine quantum mechanics with relativity, there's a massive restriction. So for spin, first of all, you're forced to talk about spin. So you have to consider quantum mechanics. That way you can take it or leave it. Now you have to, okay? And the deep consequences. Before we had in quantum mechanics, we had these two particles, fermions, bosons, totally unrelated to spin. Now there's a clear relationship. Things that have integer spin, okay, that are 0, 1, 2, those are bosons. Okay, things that have half integer spin, half, 3 halves, etc., those are fermions. Okay, so things that behave like classical waves, large collections that behave like waves, have to have integer spin. Things that behave like matter or particles have to have half integer. And not only that, there's a dramatic restriction for the number of types of particles that you can have. So in quantum mechanics, any half integer was allowed. When you include relativity, the only ones that make sense are 0, 1 half, 1, 3 halves, and 2. Okay, so it goes from an infinite possibilities to 5. Similarly with interactions, you have a continuous infinity of whatever interactions you like. Quantum mechanics dramatically restricts this. One is charge has to be conserved. So the theory violates the principles of quantum mechanics and relativity if you don't conserve charge. Things have to be local, so you can no longer have this action at distance that we talked about, where moving something very far away exerts a force on something, and by changing that, that force changes immediately. That doesn't happen. Things have to be local. Okay? So the interaction only takes place at a particular point in space-time. And to capture that, we draw these diagrams where you see, if we want to say that something's interacting with something, it happens at a point, we can draw them with these stick figures. We'll talk more, don't worry about this, we'll talk more about these in the next lectures. But these interactions have to be local, okay? So no more action distance. Another thing is there's only a finite number of specific interactions allowed. So different types of particles can interact willy-nilly with one another. You can only have these three types, okay? So the black things are bosons, the red are fermions. So you can only have, you should think of this again as space and time, but you can only have two bosons interacting with one another, three bosons interacting, or sorry, four interacting here, three, or you can have two fermions interacting with one boson. That's it, okay? So, really this is forced on you just by these basic principles. So in any conceivable world, these rules have to be applied, not just in our particular version of this. Okay, so as I said, this is really the basic framework for any possible theory. Okay, and next time we'll talk more about what our particular world is made of. So what are the things that are in it, and we know how they must behave based on this, and we'll see how how these rules really restrict things that are possible and allow us to make sense of what we actually see in our world. Okay, so I went a little bit over, but I think I'll end on there now. Okay, so maybe because it's late, maybe we'll take questions for another 5 minutes, and then people can come down at the end from there.
How close is local?
So the question was, how close is local? And local depends on it's from the uncertainty principle. So local, it's depending on the accuracy of the measurements in momentum. Right? So if you know momentum very precisely, then it doesn't have to be that local in space. But if you really want it to be local in space, then there's this big uncertainty in the momentum. So it's always this uncertainty principle that's dictating locality.
Could local mean 1,000,000 miles?
Local could mean 1,000,000 miles if you know the position or if you know the momentum to an incredible accuracy. There's a question here.
You talked about charge conjugation and time reversal. What does parity come into this?
So I did. So the question was, I talked about charge conjugation and time reversal, and I think the answer is I didn't talk about that. I talked about charge conservation. So the fact that you couldn't have an interaction that created or destroyed charge.
But maybe when we're talking about charge, we interpret the lack of causality as causality with charge.
Yeah. So yeah, I guess there's an extent to which you could say that the requirement of antiparticles is this charge conjugation thing. Sure.
Parity.
So parity comes into it. Yeah. Parity comes into it. I don't want to talk about that now because I haven't introduced parity or something, but that will come back in another lecture. There's a question from up here.
Could you go back to the slide that has E equals MC squared in it?
I hope there's not a typo in this.
Okay, I've seen this second equation with the E squared a number of times. Shouldn't there also be a potential energy term in that?
Right. So this is for a free particle. So this is for a particle that's not interacting. If it's interacting in a system, so if it's an electron in an atom, then this is not the energy. The energy has a potential energy. This is something that you can consider free. So before it interacts or after it interacts and it's moving away, this is the energy that's described to it. But you're absolutely right. If there's an interaction that's occurring, or if there's another particle that's very close, this will be modified in very complicated ways. But that's true. So in solids in particular, this is changed. Question here?
Is spin at all related to polarization, or are they two separate concepts? And if so, what exactly is the difference expressed either by a classical analog or the true quantum mechanical concept?
Right. So the question is spin related to polarization, and to what extent? And so the answer is there is a relationship. So things that are, so we think spin is just a very fundamental property of a particle. So one of the labels that a particle can have is its spin. And it turns out that when you do calculations, or when you even look at things that have spin, for light, you can say that light is spinning in one direction or the other, and by that we mean polarization. So so if light didn't have a spin, if photons, the quantum particles that make up light, didn't have a spin, it wouldn't make sense to talk about polarization. So it only makes sense to talk about polarization if a particle has a spin. So there's definitely a relationship there. But usually when we're worried about polarization, we're worried about what particular direction the spin is spinning in. And so it's very intimately related. In classical analogs, because the things that make up light are bosons, they behave like classical waves. And so you can ask sort of in what direction is the wave oscillating. So if the wave is coming at you, is it oscillating up and down like this, or left and right like this? And that is what we mean by polarization. That's sort of a classical analog, and it's related to the direction that the individual quantum particles are spinning. Okay, any further questions? Okay, so if not, then we'll talk more about how to apply this to what's in our universe next time.